Hello everyone, my name is Gemma Visitacion. Today we will talk about atoms. Okay, the word atom seems familiar to you already, but we will dig into deeper side of it, of what is an atom, how do we know atom? Atoms are said to be the fundamental unit of chemistry. Okay, let's take an example. A pizza. Pizza are made up of a variety of delicious ingredients, just like the atom. Atoms that make up matter are made up of a variety of different forms. Scientists discovered 118 different types of atoms, which we refer as elements, which are included in the periodic table of elements. A single atom is so tiny that it cannot be seen by the naked eye. But what evidence does science have that atoms really exist? To find out, let us travel back in time to ancient Greece and encounter Democritus. Many historians credited Democritus for being the first to explicitly propose the concept of an atom. In his day, it was thought that if you chopped a piece of matter, let's say watermelon, you might just keep chopping forever and ever because there was no end to its smallness. But this concept did not sit well with Democritus for reasons historians disagree on him. Instead, he insisted that you would eventually meet particles that were too small and indestructible to separate any further. It is where the word atomos is born. The word atomos or atom is a Greek word that means uncuttable. Democritus didn't have any evidence to back up his point, and as a result, many people simply dismissed it. Something that can be argued without proof can also be rejected with proof. Let us fast forward a few hundred years and visit the Arabic world. You're probably aware that you can remove salt from seawater by allowing it to evaporate or dry. People had been doing this but were unaware of it. But alchemist Jobber and others who followed in his footsteps brought extraction of science to a whole new level through meticulous research, developing complex filtration processes based on boiling vapor collection and cooling. Marie-Anne Poulsen and Antoine van Lavoisier, a French husband and a wife team, studied and expanded on the work of their Arabic forefathers in the 1700s. They discovered that chemical reactions could break down those pure substances even more. Water, for example, may be boiled to produce steam, which is still water, or separated into two pure gases. You have hydrogen and oxygen. Since the couple was unable to reduce oxygen or hydrogen to simpler gases, no matter how hard they tried, they concluded that the gases must be elements. Okay, elements are primary constituents of matter that cannot be created or broken down through normal chemical reactions. Fundamental chemicals that can be produced by combining other chemicals and can be broken down further. With this in mind, scientists all over the world started looking for and listing as many elements as they could. Finally, finding all 118 elements listed in the periodic table, some of which are gases at room temperature, just like oxygen and hydrogen, and others which are solids, such as carbon and gold. Others, such as mercury and bromine, are also liquid at room temperature. It was also discovered that when some elements are mixed together under the right pressure and temperature, they react to form new substances with new properties. The elements oxygen and iron can react to form rust. Oxygen and mercury can react to form a poisonous orange powder. And oxygen and hydrogen can react to form a clear, refreshing liquid, which we actually already knew as water. Despite the complexity of the steps, both of these reactions can be reversed. Elements can be separated, and the amount of each product we get back after separation is still the same as the amount that reacted to form the compound in the first place. The elements are true and seem indestructible, but what are they made of? Can you look, for example, try to look closer in a single ounce of pure gold and say nothing but infinity in pure gold. John Dalton, an English schoolteacher, became obsessed with chemistry in the early 1800s. In addition to performing his own experiments, he read about every experiment he could find. Paying close attention to the amounts of each product consumed in each chemical reaction, these numbers he was surprised to find a pattern emerge when two elements can react to form multiple types of compounds. They always do so in small whole number ratios in this example here. We see that in order to transform a gram of carbon into pure carbon monoxide, we need to add 1.33 grams of oxygen to turn a gram of carbon into pure carbon dioxide, that is 2.66 grams. This and many similar observations strongly suggest that oxygen and other elements are made up of tiny indivisible units called atoms. He didn't know the exact size of an atom, but the number indicated that the atoms of a single element were approximately equal in size but different in size from the atoms contained in other elements. In 1808, he wrote a book that briefly mentioned his discovery. It even came with some quite beautiful drawings. While scientists were not fully convinced that atoms were real, did they find the concept of atoms extremely useful? It helped them make accurate predictions and perform cleaner chemical reactions. Here comes Albert Einstein, suggested an experiment and developed an equation that could be used not only to prove the presence of atoms but also to calculate their exact size. A few years later, French physicist Jean Perrin used the Einstein principle to actually conduct the experiments, proving beyond reasonable doubt the existence of atoms to at least two other physicists and mathematicians that atoms do in fact exist. Atoms are much too small to be seen with ordinary light. Since the wavelength of light is too long, ordinary microscopes cannot see atoms. A group of engineers led by Sir Gerd Bennig started working on the scanning tunneling microscope in the 1970s. They hoped that a microscope would allow them to take undistorted pictures of a variety of atoms. It works by scanning and essentially feeling the surface of the sample, similar to how you would feel around in the dark to get a picture of your surroundings. This is a true scan of silicon atoms forming a crystal surface. The colors aren't real, but the data is accurate and shows the actual pattern of silicon atoms arranged in the sample. While this data is useful, scientists needed more. To that end, a team led by Dr. Ara Apkarian of the National Science Foundation's Castle Research Center discovered how to see atoms using real light. Since the wavelength of light is so much larger than an atom, this idea was previously unthinkable. But by aiming at the tip of a probe in a modified scanning tunneling microscope, they were able to effectively shrink the light wavelength and allowed it to scatter off the sample onto a detection screen. They were able to piece together this picture of a single nitrogen atom by shifting the sample bit by bit and hitting it with light each time. If we smooth out each pixel representing an individual data point from the scan, we scan we can see how similar Jan Dalton's old drawings were to fact. We now have clear visual proof that atoms exist, over 2,000 years after Democritus first suggested the concept of an atom. In conclusion, atoms are the basic components of chemistry. What evidence do we have that they exist? Chemical reactions allow us to observe their effects using mathematical equations and indirect measurements. measure their various sizes, and finally see atoms using modern technologies such as the scanning tunneling microscope, despite the fact that the term atom technically means uncuttable. Atoms are the fundamental building blocks of matter and the structural elements. Since atoms were once considered to be the smallest objects in the universe and could not be separated, the name atom derives from the Greek word or for indivisible. Atoms are now known to be made up of three particles called protons, neutrons, and electrons, each of which is made up of even smaller particles called quarks. That's all for today. Thank you.